So our lesson today is about continuity. I don't have a note outline for you guys on this one, and there aren't a terrible ton of notes. But you guys will have to either get out a piece of paper or work on Notability, whatever you want to do to store these notes. But like I said, today's lesson is about continuity. What does it mean for a function to be continuous? And that continuity comes into play a lot in this whole study of calculus. But I want you to think about, in your own words, what makes a function continuous? Like if you had to explain to someone what it means for a function to be continuous, just think about what you would say to that person. I just want you to think for a second. What would you tell a person it means for a function to be continuous? And you probably have a picture of what it would be in your mind, right? But it's hard to explain. You might say something like, you could draw it without ever picking up your pencil, or there's no breaks in the graph, or just layman's terms like that. But continuity has a very specific definition. Everything in math has a definition. So even though you might know what it means for something to be continuous, the AP exam might ask you a question. They might give you a function and say, is this function continuous? And you can't just say, yes, because I can draw it without ever lifting my pencil. There are conditions that need to be met for a function to be continuous, and that is what they were looking for, the mathematical definition of continuity. So here's the definition for a function to be continuous. Definition. Try to be able to write so you can see while I'm writing. So a function f, we'll just name it f. No, that didn't work out. A function f is said to be continuous at x equals c, so some point, if the following conditions are met. Now, in order for a function to be continuous over the entire interval, it has to be continuous at every single point in that interval. So that's why we discuss continuity at a particular point, because if a function is continuous at every single x value, then it's continuous over the entire interval. So let's see about these conditions. Well, first of all, f of c has to exist, which makes sense. The function has to exist at that x value. So for instance, if I gave some graph like this, put a hole there and then kept going and called that c, well, the function doesn't exist at c. Therefore, it wouldn't be continuous at c. So the y value has to be there. So that's condition number one. It's pretty intuitive. Okay. Well, that's not the only thing that has to be true. There are two other conditions. Second thing, the limit of the function as x approaches c must exist. The limit of the function as x approaches c must exist. And remember what that means. In order for a limit to exist, the limit from both sides must be equal. So in order for a limit of a function as x approaches c to exist, the limit of the function as you approach c from the left and the right have to be equal to each other. So where this would come into play, so think about this. I can draw a graph that meets condition 1 but breaks condition 2. And intuitively, you'll see it's not continuous. If I draw a function like this, and call that right there c. Well, f of c exists. This meets condition 1. The function exists at c. It's whatever this y value is here. But the limit doesn't exist. As I approach c from the left and the right, I don't approach the same value. So here's a case that meets condition 1 but breaks condition 2. So that must mean that there has to be a third thing that's true. Because this graph here, the second condition is met, the limit exists from both sides, but the function doesn't. So here's a case where condition 2 is met and condition 1 is broken. So let's think about what the third thing must be. And it's always good for you guys to try to think about what else has to be true to be continuous at a point? Well, the third thing that has to be true, the limit of the function as x approaches c has to equal f of c. So where the function exists, the limit has to exist as well. They have to be equal. Those two things have to be equal to one another. So here's a case. I have something like this. Here's a case that meets condition 1 and 2. Right? The function exists at c. It's this closed circle. The limit exists as x approaches c. It's whatever this y value is right here. So 1 and 2 are met. But what this third condition does, it takes where the function exists and puts it where that hole is. And then you can see we've met all the conditions. The function exists here, the limit exists there, and the function is equal to the limit. And so we have continuity right there at that point. And if a function is continuous at every single x value in the interval, it has to be a continuous function. So these are the three things that have to be true. The function must exist at that c value, the limit must exist at that c value, and the limit must be equal to the function itself at that c value. So that's the definition of continuity. So it's a little more involved than just saying you can draw it without picking up your pencil, or there's no breaks in the graph. Okay? So what I want you to do now, and you could just write these answers on the notes here. So I have 4 graphs. All right, and this is an activity that's located on Canvas as well, but I'll just put it here. There's 4 graphs here. And it says, which functions are continuous? If a function is not continuous, mathematically explain why. And in fact, I want to just have you explain why regardless. I want you to, so you're going to say yes or no on all these. They either are continuous or not, and explain why. Okay, so I want you to pause this in just a second. Now, they're going to be very easily seen if they are continuous or not. You're going to look at all 3 and that aren't continuous and know immediately. But I want you to write why. So pause the video, write your answers, and then I'll display the answers once you're done. Okay, so make sure that you are naming your functions appropriately. I know in math most things are named f, and then if f is already used, g will then be used. But notice that these functions have different names, and you have to get in the habit of naming things appropriately. Okay, so let's look at number 1. Well, 1 is obviously not continuous, but the reason being is that f of c doesn't exist. The limit as x approaches c exists, it's a, but f of c is not defined. So you could say something like f of c does not exist. You would say not continuous, f of c doesn't exist. The second one, well, g of c exists, it's b, but the limit of g as x approaches c does not exist. So even though g of c exists, the limit does not exist. Therefore, it's not continuous because it's not continuous at c. Here, the function exists at c, the limit exists as x approaches c, but make sure you stated this appropriately. H of c does not equal the limit of h as x approaches c. We have to get comfortable writing notation. Don't just write out the limit does not equal the function or things like that. You have to use appropriate mathematical notation. H of c does not equal the limit of h as x approaches c. And 4, this one is continuous. And then I asked you to explain why. Well, j of c exists, the limit of j as x approaches c exists, and j of c is equal to the limit of j as x approaches c. Here's your 3 conditions that have to be met. All right. So moving on, if a function is not continuous, there are said to be 2 types of discontinuities. Okay, there's 2 types of discontinuities. Type 1 is said to be a removable discontinuity. You have a removable discontinuity. And you may have talked about this in pre-cal, but a removable discontinuity is a hole. The reason it's removable, if you think back to last lesson that we did when we factored and canceled, we eliminated the hole. You essentially filled the hole in. And so a removable discontinuity is a hole because you can factor and cancel and remove the hole. The other type is non-removable. There's two types of non-removable discontinuities. You can have a jump discontinuity. That's like this one right here. You know, you're moving along the curve and then you have to jump to get to the other portion of the curve. That's a jump discontinuity. And then the other one is a vertical asymptote. Don't just say asymptote, but it's got to be a vertical asymptote. There's two types of asymptotes. So you'll never, if ever you're talking about asymptotes, you never just say it has an asymptote. You have to say it has a horizontal or a vertical. So those are the non-removable. You can't remove a jump or a vertical asymptote. Okay, next thing we're going to discuss is, in all these examples that we've done so far, we've been able to approach our x value from the left and from the right. And that's how we've been able to talk about, the limit existing. But what if you're talking about a function being continuous on a closed interval? Okay, like what if c, here's what I mean by that. Let's say I have this example. We have some function, let's call it square root of 9 minus x squared. And this is going to be a semicircle, top half of a circle, from -3 to 3. Okay. So our closed interval is -3 to 3. That's what we're talking about here. And how do we know if a function is continuous at an endpoint? Right? We know how to figure out if a function is continuous at a point. The function has to exist there, the limit has to exist there, and the function and the limit have to be equal. Well, if we can't approach 3 from the right, then we can't necessarily talk about the limit existing, because for a limit to exist, you have to approach it from the left and the right, and those values have to be equal. So here's kind of what we do with a one-sided limit. Okay, here's how we determine if a function exists at an endpoint, is really what we're trying to decide. Does a function exist at an endpoint? So here's a definition. So a function f is continuous on a closed interval, a to b, if it is continuous on the open interval, a to b, and I'll stop here and let you catch up here and try to make sense of this. So we're talking about a function being continuous on a closed interval. What a closed interval means, it means at the endpoints as well. Like the brackets, remember, mean you're including the endpoints. Well, first of all, it has to be continuous on the open interval. If a function is going to be continuous at all the x values in this interval, it first has to be continuous at all the x values not at the endpoint. So like if I had this graph here, I first have to know that this graph is continuous everywhere not at the endpoints. Okay? But now we need to discuss about what about the endpoints? Well, here's the next thing that has to be true. So and the limit as x approaches a from the right that must equal f of a. So we're talking about one-sided limits here, and I'll explain what this means here in a second. And the limit as x approaches b from the left of f of x has to equal f of b. So let me explain what this means. So if all this is true, then a function is continuous on the entire closed interval. Okay? So here's what all this is talking about. Okay? If I have some function, similar to the one above, I'm just going to draw a graph though. All right? And let's say I did this. Okay? So I have this function, and at the endpoints here, I have open circles, but I define that function right here, just kind of above. So you can look at it and say, well, this is not a continuous function on the closed interval, but try to think about why. Okay? The function exists everywhere on the closed interval. At any x value, we're going to call this a, call this b. At any point from a to b, including a and b, the function exists. All right? But these conditions aren't met. Right here, think about what these are doing and what these are saying. This is saying the limit of your function as x approaches a from the right. That's what this is saying. As I approach the left endpoint from the right, in order to be continuous there, the function has to be equal to whatever that limit is. So notice as I approach a from the right, the limit is 0. But f of a is whatever this y value is. So what this does, it takes this circle here, this closed circle, and basically fills it in. That's what this condition does there. And then this says, well, this point has to be at what that limit is. So basically, in order for a function to be continuous on a closed interval, your points have to exist on that at the endpoints, but also where they exist must be equal to that limit. Okay? And I think you'll get some questions about that. So, all right, so we've talked about continuity. You first need to talk about a function being continuous at all the points, and this is what that means. These conditions must be met. But if you're on a closed interval, well, the function has to be continuous everywhere inside the interval, not at the endpoints. And then at the endpoints, these two things have to be true as well. All right. Have fun.